The second week, we went through the Marina Bay Sands background and design issues. And last week, we talked about the foundation and the excavation phase. Today, we're going to start with the construction of the hotel towers. Before starting this week's presentation, we are going to briefly review the foundation of Marina Bay Sands Hotel. Let's start. The Marina Bay Sands is located on reclaimed land, which is newly created. The land consists of a large marine clay layer. This layer introduced two main problems for the construction. One was that it was way too soft to support the weight of the building without causing large differential settlements. The second problem was the large horizontal ground pressure. We introduced three construction methods that have been used to solve these two main problems, such as the deep foundation method, circular diaphragm wall, and the jet crowding. Today, we are going to talk about how the hotel towers were built on this foundation. The main design concept for the hotel was the idea that the towers should resemble poker cards. This idea was further developed into three different hotel towers, each with a unique and different inclination, and Tower 1 has, as a result of this design concept, a very sharp angle of 52 degrees for the sloping structure. The sloping structure of Tower 1 stands on its own until it reaches the 23rd floor, where it is supported by the more vertical structure. According to various computer simulations, the angle is so sharp that the structure would collapse before even getting to the 8th floor. This raised the question how it was possible to build this without collapsing. Let's think about it. First, how about plenty of columns between each floor? The first idea suggested was to put columns to support each of the floors. However, this idea was discontinued as the engineers found that they would need an astonishing number of columns, making the idea unfeasible. So how about pulling it from the outside in the opposite direction? The idea was to pull the building from the outside using a guy wire. Actually, this idea was very clever, but it was impossible in real life. Did you remember a highway was passing right next to the Marina Bay Sands site? For one, the guy wire would have to be really long in order to reach the construction site, and two, the wire would have to be anchored at a depth of 50 to 60 meters below the ground surface. Thus, it would be impossible to remove the wire once the construction was finished. The problem was back to square one. Even if this was possible, numerous temporary equipment or structures would have to be used, increasing the cost and construction period. So, how did they solve the problem? The key is the post-tensioning method. Let's study what the post-tensioning method is, with three keywords: pre-stressed concrete, vertical post-tensioning method, and high-strength concrete. First, let's do a simple experiment. Imagine a structure in which a rubber band holds up a number of blocks. If the rubber bands are loose, due to the absence of a tensile force, the blocks are easily pulled down, even with the small weight itself. However, if the tensile force is applied to both ends of the rubber bands, it's easy to see that the blocks are less saggy than before. This is the key principle of post-tensioning. Now, let's suppose this block is a concrete element. First, we talked about what pre-stressed concrete is, because post-tension is simply a type of pre-stressed concrete, which literally means applying a compression force to the concrete element in advance before it is installed. Pre-stressing a concrete structure is pretty simple. First, you stretch the steel to give it a tensile force. Second, you release the steel. Then, compressive stress will arch the concrete. Third, when loads are applied onto the concrete, the deflection will be minimized, and as a result, it's possible for the concrete element to withstand higher loads. Pre-stressing is divided into pre- and post-tensioning, depending on when the tensile force is applied. If the force is applied before casting the concrete, it's called pre-tension, and if it's applied after casting the concrete, it's called post-tension. Let's study the pre-tension method first. This is a strand, or sometimes called tendon, and consists of twisted steel wires. The strand is used to take up the tensile forces into the concrete. The strand is 5 times as strong as a regular rebar rod, and also has the advantage of being flexible. At one point, at one side of the strand, an anchor is installed, and on the other end, a load force of 133 kN is applied. Depending on the type of element, it's possible to have 70 or 80 strands in a structure. Then you cast the concrete around it and release the load. And the strand is shortened, applying compression force into the concrete. This is the process of pre-tension, literally pre. Next, let's talk about the post-tensioning and how to make the system. First, you cast the concrete with something called a duct. The inside of the duct is hollow. That duct can be filled with a strand or a large number of strands. One side of the strand is fixed with an anchor, and the other side is free. Then, the concrete is being casted in place, and similar to pre-tensioning method, the strand is stretched by using a hydraulic ram and released. Then, the compression force is applied to the concrete. One thing different with pre-tension is that casting the concrete in advance and next tensile force is applied. To summarize, the pre-stressed concrete is divided into pre or post-tension, depending on the time of casting the concrete. Pre-tension is mainly used in factories because it needs a stressing bed, which enables mass manufacturing and a high reliability of quality. However, it's not possible to make a large member because it's difficult to arrange the tendon or strands into a curved shape. Therefore, it is used to make beams that are repeatedly used again and again. Post-tensioning is used in the field and can freely customize its shape because the tensile force is applied after casting the concrete. It's mainly used for large structures, such as slabs, because it's possible to arrange tendons into a curved line. The floors of the Marina Bay Sands were designed with post-tension concrete, with maximum span of 10 meters. They can eliminate the need for internal columns and reduce temporary structures, construction costs, and construction periods. This post-tension slab provided the lightest combination for the horizontal and vertical structure. However, this only solves the problem for the floors. The collapse caused by the steep slope of the building was still the biggest problem that hasn't been resolved. From a big perspective, wire-based technology was used to solve the problem. But how did they solve the road obstacle? The biggest difference was inside, not outside. They decided to pull from the inside instead of pulling from the outside of the building. In other words, the new idea was to use the post-tension techniques slightly different. The post-tension method, however, had never been used to erect a building before. Usually, it's used for horizontal structures such as slabs and beams. The steel strand is placed and runs up inside the shear wall, making it invisible once the construction has been completed and maintains the intended shape of the building. The steel strand is pulled through every wall and tightened. This is the vertical post-tension method. It was the idea of Sanyong Engineering and Construction in Korea. This was the biggest reason why Sanyong AC was selected at the time. And the vertical post-tension method was registered as a new construction technology by number 608. The steel strand was installed inside the wall of the 20th floor, and tensile force was applied every time the building went up a new floor. There were a maximum number of 96 tendons installed per tower. One wall has 12 to 14 tendons installed and can support about 400 tons of loads. The anchors were installed 4 to 5 meters below the ground surface. This is a model experiment of the vertical post tension. As you can see, if the strand is pulled, the building will stand upright. But this results into another problem. The tensile force is not only applied in the tendons, but also in the concrete walls continuously. And as you know, concrete is very vulnerable to tensile forces. Therefore, the building had to use high-strength concrete. The strength of concrete used on the RC walls of the tower is 60 megapascal until the 40th floor. Concrete with a specified strength of 40 megapascal or higher can be defined as high-strength concrete. The strength of normal concrete used in general buildings is usually 30 megapascal and can bear loads of up to 25 tons. The strength of the concrete used in the Marina Bay Sands towers is about 50 megapascal. This high-strength concrete can bear loads of up to 60 tons. Additionally, 100 megapascal concrete was used for where the anchors were installed, which can withstand loads of up to 92 tons. To summarize, the post-tension construction method and the high-strength concrete made it possible to overcome the design for the steep inclination. By using this high-strength concrete, the thickness of the building could be thinner, and the building could be built more lighter, and the aesthetic function could be obtained. Therefore, thanks to the high-strength concrete, the building could obtain both design and safety requirements. This week, we talked about the post-tension and the high-strength concrete for the hotel towers. Next week, we'll go deeper in the hotel tower construction. Thank you for watching our presentation, and until next week.